Okay, let's go for the next topic. It's gonna be particles and waves. Actually, this is quantum mechanics. The origin of quantum mechanics is these two cases. We have the photoelectric effect and we have the black body radiation. Let's start with the black body radiation. The black body radiation tell us that when we have a hot object and that object emits radiation, electromagnetic radiation, this is the behavior of that radiation. Imagine that this is for a hot object like our sun with temperature equals to 6,000 K. If the temperature decreases, also imagine that this is lambda and this is the intensity. If the wavelength increases, what happens? Well, this is the path of the object, right? Imagine that this is the temperature equals to 5,000 K and so on, right? We have another temperature, correct? Let's say 3,000 K. This peak, the maximum, is called lambda maxima, right? Means that if the temperature decreases, the lambda maxima also increases. Well, if the temperature decreases, lambda max increases. Okay, there is a relationship between lambda and temperature, and this is that relationship. Lambda maxima is equals to about 2.98 times 10 to the negative 3 meters times Kelvin divided by temperature in Kelvin. This is called the Wien's law. Wien's law. Right. Again, this is the behavior for any black body radiation. A black body is an ideal object that absorbs all the electromagnetic radiation. Actually, a good absorber is also a good emitter. So also a good emitter is considered to be a black body. Like our sun is a good emitter of the electromagnetic radiation, so we take it as a black body. Correct? Perfect. And well, this is the behavior for this black bodies or hot object. Any hot object actually emits electromagnetic radiation. For example, our body has a temperature, is hot, has some temperature, emits in the infrared. Correct, in the infrared. Perfect. Now let's study more this case. This is from the experiment. Look, in the experiment is found this behavior for a hot object. Correct. One more time. It was like in that way. But the theory, this is lambda. The theory predicts this behavior. That's the theory. Correct. This is the experiment. The experimental behavior right here. Correct. And this is the theory. As you can see, if this is lambda, and this is the intensity. When lambda decreases, or we can say that when the frequency increases, because we can use also this relationship, the speed of light is equals to frequency times lambda, correct? If lambda decreases means the frequency increases, right? The theory doesn't match the experiment. This is classical theory, right? Classical, right? Theory. So only they agree right here, right? Some wavelengths, right? Long wavelength, correct? But later, right? They don't match. By 1900, Max Planck tried to solve this problem. He said, well, actually, instead of taking the electrons, remember, an electron radiates electromagnetic energy when the electrons oscillate. The electrons are considered to be attached to springs, right? So the electrons are oscillating like the spring, back and forth, up and down, right? And in that way is the creation of the electromagnetic radiation. But according to the theory, the amplitude could be any amplitude. The energy that the electron can take could be any energy, any frequency. So it's like a continuous frequency that can be taken by any electron that oscillates inside of a hard object, right? But Max Planck said, well, instead of taking to be continuous, let's take it to be a discrete values. The electron takes only discrete values of energy, discrete values of frequency. It's like the charge, right? The charge is not continuous. The charge is quantized, right? It's quantized. The charge, remember, the charge is equals to a whole numbers of the unit charge, which is the charge of the electron. The same thing happens to the energy. The energy now is quantized. The energy that is radiated by the electrons, right, is gonna be quantized. Means that this energy, the total energy, is equals to whole numbers of this unit of energy. And this unit of energy is proportional. This energy is proportional to some frequency, right? So if the frequency increases, the energy increases. How do we eliminate this symbol? Using a constant. So this energy, right, is equals to a constant times this constant h is called the Planck's constant times the frequency. So in general, what do we have? Well, we have that energy is equals to Planck's constant times the frequency, where this is the Planck's constant equals to 6.63 times 10 to the negative 34 joules times second. Correct? Perfect. Now, again, this is the constant, Planck's constant, and using this concept, this hypothesis, Planck showed that the experiment now matches the theory. Correct? According to these ideas, one more time, this is the curve given by Max Planck, right? And these are the points given in the experiment. Correct? So in this case, this is for Max Planck. Max Planck's correct hypothesis. Correct? And this is the experiment. These that are the experimental point. So now everything matches correctly when we take the energy to be quantized. Correct? The electromagnetic energy. We're dealing in this case with electromagnetic energy. Perfect. So we have then the first part of the origin for quantum mechanics is the by radiation. It was solved by Max Planck using this relationship. Perfect. Now let's go to the next case that gives the origin, the birth of quantum physics, okay, or quantum mechanics, and that's gonna be the photoelectric effect. Photoelectric effect. This was a study at the beginning by Hertz. We're familiar to this guy, right? Hertz. He found that if we have a charged object and ultraviolet radiation is sent right to this object is discharged. Right? We can discharge this charged object by sending ultraviolet radiation to a charged object. Right? Perfect. One of his students made this experiment he used right this he isolate right a charged object using this tube right here, kind of this one, like this. Okay, uh, he charged this object. Remember how we can charge object? Well, by rubbing right to object, by contact, by induction. But this another way, using a battery. That's the idea in this case. So a battery is used. Remember when we have two plates, and we connect these two plates to a battery to create this capacitor. For example, it becomes, this is positive negative, becomes positive charged, then negative charge. Correct. So we're charging objects, similarly to this case, right? Okay, that's the situation right here. Correct. Perfect. So we have a battery right here. Correct. Potential difference, and we have to measure this the current through this circuit. Perfect. Now again, this becomes positive or negative charge, positive charge. We have ultraviolet radiation. The ultraviolet radiation removes the electrons, like in this case, right, or charged particles are removed. Right, they are removed, correct? Imagine they are removed right in many in any direction, let's say. But what happens when we have these two plates that are charged? Well, like in this case, well, we have an electric field, right? We have an electric field in between. If we take we have a charged particle like this particle. Well, this is being accelerated right to that end, right? Because of the electric field. The same thing happens right here. We have charges that are accelerated to the other electrode, right? And we create a current. Got it? We create a current. And that current increases if we increase the intensity. How we can increase the intensity? Well, if we have one lamp, we can double the lamp. If we double the lamp, we increase the amount of electrons being ejected. We increase the current. Remember, current is charge per unit time. If we triple the numbers of lamps, we increase the intensity, so we have more electrons. We have the increase of the current. Okay, perfect. Also, it's found that if we have a different frequency, let's say in the visible, no electrons are being ejected, right? Only if we are in the ultraviolet. Actually, this depends on the material, right? Depends on the material. Some materials use at this time visible, right? You have a calculator. You have here to a calculator. We have solar panels, right? That use the photoelectric effect. Correct. So it depends on the material that is used. So means one more time that some frequency, after some frequency, that is called, this frequency is called the threshold frequency. Right, this is the minimum frequency. For example, for these types of electrons, let's say it's the ultraviolet, if we are with a frequency a little bit less than the ultraviolet, well, nothing happens. But if we start at the ultraviolet, the frequency, well, we start creating the photoelectric effect. And after that, of course, we increase the amount and the speed, energy of the electrons from here to here. Correct? Perfect. Actually, also it's found that if we have some frequency like ultraviolet in this case, if we increase the voltage, the current stays the same, right? The current stays the same when we increase the voltage. Of course, we're taking fixed the frequency. But what happens if we reverse the battery? If the battery is reversed, if we increase again the voltage, it's found that the current decreasing, and there is one voltage at which the current stops. That is called the stopping voltage or the stopping potential, right? The stopping potential. Correct. Well, this is the analysis given by students of Hertz. Correct. And let's see. This case, this photoelectric effect was explained by Albert Einstein. Albert Einstein explained this effect, and because of that, he won the Nobel Prize. And this is more or less how he explained this effect, photoelectric effect. He said, well, this is similar to have a electron. This is an electron or a proton or charged particle, right? Charged particle, correct? And we have this is a or let's take the mechanics. So imagine this is a particle mass. Any particle is a rest velocity equals to 0, right? And we have some mass m. What happens if we hit this object? We use an impulse, right? Use an impulse to use a force, right? And now we move this object. What happens then? Well, when we push this object, we hit it, it gains, right, some velocity. So now it has some velocity at the beginning. If the velocity is not so large velocity, the object is gonna stop right here and returns, right? But if the velocity increases, correct, this mass is gonna be moving and it's gonna be, imagine we have with some, this is initial velocity, some final velocity. Imagine we have no friction, nothing. How do we solve this problem? Using conservation of energy, right? So what do we have at the beginning? Kinetic energy, initial kinetic energy is equals to what? Imagine this is potential energy, correct? Equals to potential energy plus what? Plus a final, right? Final kinetic energy. So that's the way how we solve this problem. In the same way, the photoelectric effect was explained by Albert Einstein. He said, well, something like this, we have the electron, imagine right here, this is the electron, this is a rest at the beginning, we have a photon. By the way, remember, Max Planck found that the energy of this electromagnetic radiation, right, is equals to this constant times the frequency. He called this energy, right, the energy of a quantum. We call it quantum. Albert Einstein called it photon. It's the same thing, photon. Now, what is a photon? Photon is the minimum quantity of energy, electromagnetic energy. It's similarly to the atoms. Remember when we have an atom right here, let's say gold, and we divide it by 2 and so on, and we go to the minimum amount of gold. The minimum amount of gold that still possess the same qualities as the original one is called the atom, right? Atom. What about if we have electromagnetic radiation? Let's say infrared. Let's say red indivisible, right? Red photon, red radiation. Okay, let's do the same thing. Let's divide this by 2, correct, and so on. Now, what do we have at the end? For the matter, well, we have the photon. Right, the photon, the minimum quantity of energy that still possess the same qualities as the original one. The same thing as for the atom. In this case, right, we have atoms of gold, aluminum, copper, iron, and so on. The same thing happens right here. We have photons, indivisible, red photons, yellow photons, blue photons, ultraviolet photons, right? X-ray photons, infrared photons, and so on. Okay, perfect. Now, we have a photon right here. If this photon hit this electron, let's say, now this electron gains some energy. What is the energy carried by this photon? This is the symbol for energy. We're gonna be energy is equals to this constant, Max Planck's constant, times the frequency of the photon. Later, of course, it has to go beyond the attraction of the atom, correct? And now the particle is right here with some kinetic energy, right? Some kinetic energy. But also, this quantity is similar to this one, and this is called the work function. Work function. Okay, that's the work function. And we have different symbols. We can use work, right? It's like the work function. So what do we have? What should be then the analysis of this effect? Well, we have at the beginning the energy of the photon is converted into what? Into this kinetic energy. Actually, this is called the maximum, right? Kinetic energy plus the work function, right? This is the work function, W naught. Correct, W naught. Also, we can use phi and so on. Perfect. So this is again the explanation for the effect, photoelectric effect, and thanks to this, Einstein won the Nobel Prize. Okay, so we have the frequency of a photon is equals to K max kinetic energy plus the work function. The work function simulates, right, the potential energy when we're dealing with mechanics. Correct? Perfect. And then this is the picture that is happening when we're dealing with the photoelectric effect. We have, imagine that this is the frequency, and then we have right here K max. One more time, remember we have the threshold frequency. After that, right, we have that if we increase the frequency, we increase the energy of the electrons or particles, that which is the electrode, correct? In that way. Perfect. Okay, again, this is the photoelectric effect. Now let's go to Compton effect. Compton effect. Okay, let's do a Compton effect. Compton effect. In this case, we have X-rays. X-rays is being sent to a crystal, and we have a reflection of X-rays, and the frequency is studied at the beginning and the end, and it's found that the frequency is less, right, when we have light or X-rays reflected. Like in this way, imagine that we have this wave, this is X-rays, and we have a material right here. Actually, what do we have? We have a crystal, so we have electron, right? Electrons, free electrons. Okay, imagine this is the electron right here. And then we have the scattering later. This is scattered X-rays, scatter, right? X-rays, correct. And then we have the recoil of the electron, correct? Recoil. Perfect, electron. Great. Now, in this case, we can see that light behaves as a particle. We know so far that light behaves as a wave, correct? And we prove that using the Young's double slit experiment. We have two slits, we have light, and we have the pattern of interference, and that's the pattern for waves. Means that light behaves as a wave. Yes, perfect. But with this using this experiment, and now it's shown that light behaves as a particle. Right? Because that's the behavior of a particle. We have some velocity, some energy, and then the energy decreases right after collision, right? Because some energy is now shared to the electron right here. Alright, so light also behaves as a particle. So actually, light behaves as waves as a particle. When light behaves as a wave, when it's traveling, and how light behaves as a particle when there is collision, impact, like in this case. Got it? That's the idea. Perfect. Now, this effect has this equation, correct? This is the way how it's found. It's kind of it's for higher levels. This is for higher levels, this analysis. But let me try to explain it right here a little bit, make an introduction. So we have a momentum. This is momentum, correct? Of the X-rays, right? We have momentum. Also, we have the momentum. Remember when we have collision right here, this is momentum, correct? Later, of course, we have the electron right here. We have the recoil, and then we have we call this lambda, right? This is momentum for lambda prime, and this is just momentum for the recoil, correct? So this is the case. This is the initial momentum. This is for the scattered momentum, right? Lambda prime, and this is gonna be for the recoil, correct? Perfect. Using the law of cosines, we can see that p lambda, correct, square plus p lambda prime square minus twice p lambda prime cosine theta, correct, is equals to p square. Correct? Perfect. And then what do we have? If we multiply, correct, by c square, it's found that this is equals to x square f square plus one more time f h square f prime square minus twice h square h is f prime, correct, cosine theta is equals to p c square, correct. And also right here we are using this relationship p c is equals to h times frequency. This is from relativity. We use this quantity again from relativity. Okay, perfect. This is when we use momentum. The same thing happens when we use energy, right? Conservation of energy. We have that energy of the photon plus this energy at rest of the particle must be equals to the final energy of the in this case the photon, the X-rays, plus this recoil energy. When we combine this, and this kind of tedious to do all the process, it's found that the change in lambda is equals to lambda prime minus lambda, and this is equals to h, the Planck's constant, divided by mass at rest of the particles times speed of light times 1 minus cosine theta. Correct? Means that we need to subtract this minus this, and that's why we have minus this quantity right here. And this is the Compton effect. Right? That's the question that is found using the relationship momentum. Remember, we mentioned in mechanics that when we have elastic collisions, we can solve the problem using conservation of momentum and or conservation of energy. This is the case when we have one unknown, but if we have two unknowns, we need to use both conservation of momentum and conservation of energy and combine them. That's the way for this case, right? We have conservation of momentum and conservation of energy, we combine them. When we combine them, we create this equation, right? That represents the Compton effect. That the light behaves as a particle. Got it? Perfect. Now let's go to the other case when particle behaves as a wave. Correct? We have the other case when particle, we know like electron, in this case electron, which is the particle behaves as, of course, as a particle, correct, but also behaves as a wave. And this is the case when we are dealing with the Broglie wavelength, the Broglie right wavelength. Okay, lambda. That's the Broglie wavelength, lambda. Look, and this is found in this way. This is from actually from relativity. We can find this easily. Momentum is equals to the Planck's constant times frequency divided by c, correct? And but what is c? Actually this is coming from this. Energy is equals to Pc. This is from relativity. It's found in the chapter of relativity. But what is the energy? The energy is max Planck's constant times frequency equals to Pc. Correct? Perfect. So momentum is equals to what from here? Momentum is Planck's constant frequency divided by c. But c, the speed of light, is also equals to frequency times the lambda. Correct? So it's equals to max Planck's constant times frequency divided by frequency divided by lambda. And this is equals to what? It's equals to is correct. From here we have c. This is not correct. This is gonna be frequency times lambda. Correct? Frequency times lambda. It's equals to just the constant times lambda. From here we can solve, right, for the wavelength, right? The Broglie wavelength, and the Broglie wavelength is equals to this constant divided by momentum. When we're dealing with electrons, of course, the momentum is mv. Correct? And this is actually the Broglie wavelength, right? The Broglie, correct, wavelength, lambda. And this is found in also experiment. If electrons are sent to this slit, where we have electrons sent to a slit, is found on the screen, right, that the electrons, the impact behaves as a interference using light, right? We have maximums and minimums, right? Like this, maximums and minimums, like this, okay. Maximums and minimums, which is the behavior of a wave. So in this case, particles, electrons, behaves also as a wave when they are traveling, right? When they're traveling, behaves as a wave. Correct? And that's the formula that helps us to study this behavior. Correct? Lambda, or the Broglie wavelength, is equals to Planck's constant divided by the mass of the electron or the proton, usually it's electron, times the speed of the electron. Correct? Perfect. And with this, we finished the analysis for this chapter, particles and waves. Okay. Thank you, and see you in the next video. Bye.